Hello, my name is Sawyer Garrity. We are group 11, and we chose to do Venmo as our the company that we wanted to do our project on. And we'll have everyone introduce themselves real quick.
Hi, I'm Lauren Cook. I'm a Mac student here at U of U, and I'm in the Accounting Information Systems track, which is why I'm in this class.
Awesome. I'm Isaac Hong. I'm a full-time MBA student and looking to get some more SQL skills, so this class was really useful.
And I'm Ashley Boren, and I'm an MSIS student.
All right, so with no further ado, we'll hop right in here. A little history on Venmo. So Venmo is a fast, safe social payment application, and a big reason why we chose Venmo is because we all already have downloaded the app and use it. So we thought it'd be interesting to kind of learn what the back end looks like. But Venmo, their mission statement is to make it easier for you to pay your friends and family. Money can be awkward, and we want you to be able to spend less time thinking about it and more time enjoying stuff that matters to you. So a little bit of history on Venmo's growth and acquisition. They were founded in 2009 by these two guys on the bottom right, Andrew's on the right and Ikram's on the left. They are friends still, but they founded Venmo as friends in college as a way to split checks in an easier fashion. But like I said, they were founded in 2009. Later, they were acquired by Braintree in 2012 for about 26 million. And then just less than a year after that, PayPal came in and acquired Venmo from Braintree, and they are currently under PayPal to this day. So as we dove into this project, we just had to decide how we wanted to limit the scope, because thinking about building out a conceptual model for all of everything that Venmo can do was very daunting and unrealistic. So we decided to just focus on the user-to-user portion of the app. So the two requirements based off of that scope were that users must have a bank account or a credit card, so some way to transfer money. And two, users must be able to make and receive payments from other users, the transaction aspect. In order to achieve our goal of accurately reverse engineering Venmo's database, there were three main components that we kind of had to focus on to feel like we were successful. And the first one was identify the proper amount of entities involved in a peer-to-peer Venmo transaction. Meaning, is this going to include users, accounts, transactions? What are all the different nouns per se that are included? Second was, how do these entities interact with each other? What kind of relationships are there between bank accounts, users, transaction? And the third was to build a database that handles routine but diverse types of transactions within the app, because we know there are millions of transactions going on every day on this app, and sometimes it's a simple payment and sometimes there's a lot of back and forth.
So what we did was we took the requirements that Sawyer went over, and this was the conceptual model that we ended up with. So as you can see here, users and their access to a bank account or a credit card is really central to our conceptual model. Users must first link their Venmo account to their bank account or valid credit card in order to make transactions with other users. There are two types of transactions that we're tracking here. The first is the peer-to-peer, and the second is the internal user to the external account. And this actually caused a pretty big hurdle for us to overcome. When we originally modeled this, we had two relationship types for the transactions. But we decided to just track with one relationship type to keep things really simple and clean. We worried that having two relationship types tracking essentially the same information would quickly become really messy when adding in the data. A key idea to this model is after a user sets up an account, you can always calculate the account balance because you have a running list of all of the positive and negative account transactions. So we'd originally considered adding this in as a weak entity type, but we made an assumption that if all the transactions were being tracked, there would always be a running total anyways, and there wasn't any need for us to duplicate that data. A few other example or elements to highlight here from our conceptual model is that users can make transactions, but they're not required to make one. We also wanted to track the ability that users have to make multiple transactions on the same day. So we updated our model to include a transaction ID attribute. Another interesting element to highlight from our model is the unary relationship type. Users make transactions with other users, so it took us quite some time to fully understand all of the nuances of modeling a relationship that has just one entity that relates back to that same entity.
All right. As Ashley was saying, well, a lot of the things that Ashley was saying, I'm going to go over again, but kind of point out how they relate to the logical model. And we wanted to create a database that was really clean and easy to understand. And we felt that we included all the essential attributes without making the model. As we walked through this process, as we worked through the process, we made improvements along the way and ended up with this. At the top, the user table, which plays a primary role in our database. This is where we gather all of the essential data that defines who the customer is. It can be seen as a foreign key in the user transaction table and the external account table. These foreign keys are essential in making our database function. In addition, we have a transactee username as a foreign key that relates to username. This foreign key name is slightly different to represent the relationship that Ashley was talking about earlier. When a unary relationship type exists, it is important where you can identify two distinct usernames within transactions. Without that distinction, the database would only transact between one user, which would present an entirely different set of problems. The table that is the largest is clearly the user transaction table. And this table came to be navigating the different relationship types through the transaction relationship type. This table is essential for transactions to occur, like stated earlier. This table records all the identifying attributes to connect transactions to specific users with a designated. We wanted to be able to identify a specific transaction, the paying user, and the receiving user. Finally, we have information about the different types of accounts. We have the external that connects users to a bank or source of money. Additionally, we have a bank table and a credit card table that will help us with money transactions. Although they have slightly different names, the bank account number and the credit card account number both represent foreign to account number, as represented by the connecting lines. These types of tables occur when they have a conceptual model with a supertype and subtypes. These accounts represent the different types of accounts a user can attach to their profile and use within transactions. As we created this logical model, we wanted to understand how complex a business's database could be. And we spent a significant amount of time on this between the four of us, and we have a limited. And this class especially started getting difficult when we actually had to implement the conceptual model and the logical model into a physical data, which I'll let Lauren talk about.
Okay, so as Isaac said, we kind of had a little bit of trouble with the physical model, just trying to see what data types fit perfectly with each attribute. And It got a little confusing on some of them, but I just want to highlight some of them. For example, account number and routing number, they are both represented by numbers. And so I had to look up and research how long an account number typically is and how long a routing number typically is. And from Google told me that an accounting number is usually 12 numbers long and a routing number is usually 9. And so I'm going to trust Google on that one. And then another one I wanted to point out is the security code. Most security codes on credit cards are only 3 numbers long. However, I've had an American Express card where the security code is actually 4 numbers long. And so I didn't want to limit any of the users into, oh, you can't put a credit card on here if it's an American Express because we can only have 3 numbers. So I made that data type 4 numbers long so that they were able to put in whatever credit card they wanted in there, whether it was Chase, whatever, American Express, whatever. The last one I wanted to talk about is the expiration date on a credit card as well.
Technical difficulties, please hold.
I think what she was, oh, are you back?
I don't know. I didn't know I left.
Can you go back like 30 seconds and repeat what you're saying?
You were just talking about the expiration date.
Yeah.
Okay, yeah. So on a credit card, an expiration date only has a month and a year. And so I made an assumption that the day of the expiration date is going to be the 31st or the 30th or the 28th if you're in February of the month, the last day of the month, I guess.
Awesome. So future ideas, we would love to be able to social media elements of Venmo, transaction descriptions, comments, and likes, because these are the more interesting aspects of Venmo. With our basic understanding that we gained in this class, we recognize that's a big lift, and we'll probably leave that for a future day. And then the second aspect we would like to include is paying merchants through Venmo, which I originally didn't know that you could even do through Venmo. So I am personally interested in looking at this. But as we did this project together as a team, we realized just how much work went into building a database. But we all feel like this was extremely beneficial and will be great for our futures. So we hope that you learned a little bit more about Venmo.